Hi, I'm Coach Cowland, and in this presentation, we're going to look at linear momentum. Some things to know about momentum. So first of all, momentum comes in two flavors. It comes in linear and angular. Currently, we're going to look at linear momentum, and later on, we'll look at angular momentum in a different video. Um, Anything that is moving has momentum. Well, technically, anything that's moving and has mass has momentum. Linear momentum comes from Newton's laws of motion. And in the third video, you'll see how they transpire. And linear momentum is proportional to velocity and is proportional to mass. So here's the equation for linear momentum. The unit for momentum, the variable for momentum is lowercase p. P is equal to, or momentum is equal to mv, mass times velocity. And the units for momentum, uninterestingly, are the units of mass multiplied by the units of velocity. So that's kilograms meters per second. So conservation of linear momentum. Conservation laws are all important in physics. They help us work out so many things. And conservation of linear momentum says that if a system is closed, that means that it's not affected by any forces external to it, then the momentum that you start with is equal to the momentum that you end with. This is really important and helps us to be able to figure out so many things. Without this, physics just wouldn't be the same. So here's a great example of a conservation of linear momentum. In a Newton's cradle, all of the balls that are attached to the wires have the same mass. Let's say that mass is a mass m. When the first ball strikes the second one, it has a velocity of v. Don't know what that is, but let's just say it has a velocity of v. That means its momentum at impact is mv. We know all of the balls in the cradle have the same mass. So the momentum of that first ball when it strikes has to go somewhere. So it's basically effectively passed along the line until it gets to the next ball. Now each time it hits one ball, it passes that momentum to the next one. For an instant, you could say, I suppose, that it goes at a velocity v until it hits the next ball. And of course, but because they're in contact, it keeps on going. The only one that's free to move is the very end one, and that leaves with the same velocity v as the first one that struck it. Now, um, gravity turns that around and brings that back again, so that when it strikes the ball on the ball next to it, it has a velocity v, and of course we know it has a mass m, and it passes it back down the line. Now, if it's a perfect system and there's no forces like friction or anything else there that would cause it to slow down, then this would continue just like this graphic is showing forever. Unfortunately, in the real world, there are other forces that take some of that energy away, and momentum is it's not a closed system, so the linear momentum will decrease. So we got two cars here, and both of them have a mass of 1500 kilograms. So which one has the greater linear momentum? If I hit play, quite clearly the red car went a bit faster than the blue car. So that means that obviously its velocity was greater. It's got a greater velocity multiplied by the same mass. Even though the masses are the same, it has a greater linear momentum. What about this one? We have an airplane here with a mass of 4,500 kilograms and a basketball with a mass of 1.5 kilograms. And I'll hit play. Okay, the mass of the airplane really high, but what's its velocity? It's zero. So if you multiply anything by zero, you get zero. So that means that the momentum of the aircraft is zero. The momentum of the ball, it actually has a momentum because neither the mass nor the velocity are equal to zero. So here we have a ball and a plane and a car. Um, which one has the greater linear momentum? I'm going to hit play. Okay, here we saw the ball went a little bit faster than the car did, but the car is 1,000 times more massive. So unless the ball went 1,000 times faster than the car, which it didn't look like it did, um, then the momentum is going to be greater for the car than it is for the ball. So here, let's do some examples. The mass of a bullet is 8 grams and it has a velocity of 500 meters per second. What is its momentum? Part 2 is if a vehicle weighs 2,000 kilograms, what velocity would it have to travel to have the same momentum as the bullet we talked about in the first part? So first of all, let's look at the bullet. 8 grams, when we convert that to SI units, remember we always use SI units when dealing with this kind of thing, we get a mass of 0.008 kilograms. And we know that P is equal to mv, so we're going to multiply that by 500. And that gives us a momentum P of 4 kilogram meters per second. It's not a very high value. So the vehicle. The vehicle has a very high mass, and we know what the momentum is going to be, so what we need to do is take P equals mv and rearrange it and make v the subject. So the velocity in this case is the momentum divided by the mass. So the momentum of the bullet was 4 kilograms meters per second. When we divide that by the 2,000 kilograms that the vehicle weighs, we get a velocity of 0.02 meters per second, which is extremely slow. That's about 2 millimeters per second. Wow. Okay, different example this time. A truck with only a driver in it weighs 2,200 kilograms. What is its momentum when it's traveling 6 meters per second? And then the truck is loaded with 460 kilograms of cargo and is traveling at the same speed. What is its new momentum? The first part, the momentum of the truck with the driver is 2,200 multiplied by 6. It's traveling at 6 meters per second. Straightforward calculation. 13,200 kilogram meters per second. That's its momentum, just the empty truck. When the truck is loaded, we need to add 460 to the mass of the truck. So it's 2,200 plus 460, which makes 2,660. 6 times 2,660 is 15,960 kilograms meters per second. So that's a significant increase. Okay, thanks for watching, and in the next presentation we'll look at collisions.